Hello everyone, welcome back to Geeks for Geeks, and in today's video we'll be discussing our weekly contest 183. We will be discussing all the 4 problems that were there in our weekly contest 183. So let's start with our first problem. The name of our problem 1 was seating arrangement. Let's read the problem statement. In a classroom there are k benches and n students. Almost m students can sit on each bench, but students prefer to sit alone to focus better on their studies. Your task is to find the maximum number of students who can sit alone on separate benches such that all n students are to be seated. If it is impossible for all students to sit in the classroom under the given rules, return -1. So we have given k benches and n students, and almost m students can sit on each bench. So we have to tell if all n students sits on those k benches, how many students we will be able to sit such that only a single student will be sitting on a single bench, right? If we have something like 4 benches and on each bench, let's say 4 students can sit. So we have to make sitting arrangement such that the maximum number of students will be sitting alone, right? Let's say we have to sit 11 students. So no, not 11, let's say we have to sit 10 students. So if we have 4 benches and each bench is able to hold 4 students, so if we sit 4 students here and 4 students are sitting here, then we are left with 2 students. So those two students can sit alone, right? So 2 will be the maximum number of students that can sit alone. So if we had something like 18, right? So let's 4 students will be sitting here, 4 students will be sitting here, but still the total is 16. We already left with 2 students. So there's no possible way to make all the n students sit. Then in that case we will be returning -1. So let's see an example. So we have here k equals to 4. So we have 4 benches. So on each bench I can sit 7 students. 1, 2, 3, 4, 5, 6, 7, and we have a total of 20 students. So we have to find maximum number of students which can sit alone, right? A single student will be sitting on a single bench. So if 7 students sits here, if 7 students sit here, and now I'm left with 14 students done, I'm left with 6 students. Then out of those 6 students, 5 students sit here, then our 1 student can sit alone, right? That's how we can make the sitting arrangement, and the output for this example will be 1, right? Because whatever we do, we have, like, this bench has the maximum capacity, this bench has now the maximum capacity, 14 students seated, I'm left with 6. Now out of those 6, if I make 1 student sit here, then I'll be left with 5. I have to make other 5 students sit on the next bench, right? I can't make more than 1 student sit alone in this test case, right? Let's take one more example. Here we have similarly 4 benches, and each bench can hold up to 3 students. Each bench has 3 seats, and we have a total of 20 students. So here, if we make 3 students sit here, 3 here, 3 here, 3 here, it gives me a total of 12. So I won't be able to make 20 students sit in these 4 benches. So in that case, I'll return -1. So the output will be -1, right? That's what we have to do. We have to make the sitting arrangement such that maximum number of students will be able to sit alone, and if it is possible to make all the students sit on the number of benches given, so I have to make all the students sit, and out of that I have to return maximum number of students who are sitting alone. So let's see what are the different cases we can have in this question. So now the different cases that we can have in this question can be if the total capacity is less than number of students. Right, this can be our first case. What does this mean? If the total capacity, let's say we have k benches, and each bench is holding m students, so the total capacity will be k into m, right? At most I'll be able to make k into m students sit, but what if my total number of students is larger than total capacity k into m, right? Why is the total capacity k into m? Because k is the number of benches I have and m is the sitting capacity of each bench, so this will give me the sitting capacity of total benches. So if the number of students I have is greater than my total sitting capacity, then I won't be able to make all the students sit. So if number of students is greater than total sitting capacity, then what I'll do, I'll return -1, right? Then the particular case is not feasible. There's no way I'll be able to make all the students sit. In that case, I'll return -1, right? So next case we have if the number of students that can sit on each bench is 1. What does this test case say? If like we have some 10 benches and the maximum number of students that I can make on each bench sit is only 1, right? So in that case, the, the maximum number of student and the student I have to make sit is equal, right? I have to make one student sit, make a student sit alone, and the maximum number of students that can sit is also 1. So in that case, what I'll do, if the total sitting capacity is if the total sitting capacity is greater or equal to number of students, then I'll return the number of students, because if all the students are able to sit, then all the students will be sitting alone, right? So in that case, I'll return 1. Let's say if mm, m equals to 1, right? This is the maximum number of students that can sit. I'll return my total number of students, return n. Here the maximum number of students that can sit was also 1. So whatever I'll do, I can't make more than one student sit on each bench. So if it is feasible for all the students to sit on all the benches, then the total number of students that would be sitting alone will be equal to the total number of students, right? Let's see our third case. So if the number of benches we have is greater than number of students, right? What does this mean? If let's say we have 20 benches and the number of students that we have to sit is only 16, then what we will do, then we have to do nothing, then we will be just returning our total number of students that we have. Why? Because no matter what is the maximum m we have, we can make all the students sit alone normally, right? All the students will be able to sit alone. Let's say if this m is 10, 11 or something else, we know that our m will be either equal to 1 or greater than 1. This is the initial condition of m. So we know that at least one student can sit on each bench, and if the number of benches we have is greater than number of students, then we can surely make all the students sit alone. So if k is greater than equals to n, then we will return n. So now these were the base cases, these were the special cases and base cases. Like here, if the total capacity is less than number of students, and if number of students the maximum number of students that we can sit on each bench was 1, and if the number of benches was greater than the number of students. Now let's see how we are going to calculate the number of students who will be sitting alone, right? So here we will be forming some mathematical equation. Firstly, let's assume that the total number of students that sit alone is x, right? Currently we have to find what are the total number of students that are sitting alone, total alone students. So we don't know that. So initially we will be taking it as x. Now number of remaining benches. So if x students are sitting alone, then what will be the remaining benches? The remaining benches will be k minus x, right? Because x students will be taking x benches as they are sitting alone. So the remaining benches that I'll have will be k minus x, total number of benches and the occupied benches. Remaining seats will be the seats that will be remained. So if each bench is able to hold m students, so what is the total number of seats that I'll be left with? So remaining benches into the capacity of each bench into m, right? This will be the remaining seats that I'll have. And what will be the remaining students? So if x students are sitting alone, then n minus x students will be sitting together, not alone, right? They can be in a pair, or they can be sitting 3 together, 4 together, up to m, right? So if now I need to form, I have to make all these remaining students sit on the remaining seats, right? So to all these remaining students sit on these remaining seats, this the remaining students should be smaller than or equal to the remaining seats, right? Because if the number of seats I have is smaller than the number of remaining students, then the x I found is not correct, right? Because if the remaining students is lesser than, if the remaining students is more than remaining seats, then I won't be able to make all the students sit on their seat. Then the x that I found is incorrect, right? So I have to make all the remaining students sit on the remaining seats. So for that, this will be my condition: n minus x, which is the remaining seats, should be lesser than k minus x into m, which is the remaining seats. So the remaining student should be either lesser or equal to the remaining seats, so that all the remaining students will be able to sit on the remaining seats. Now let's simplify this. Let's see what we will get. N minus x is lesser than or equals to k into m minus x into m. Now let's take x on similar sides. Now minus n minus k is lesser than or equals to x minus x into m. Sorry, k into m, it will be k into m, right? And n minus k into m will be lesser than or equals to, let's take x common, 1 minus m. So the value of x should be greater than or equal to this, right? Now with the help of this, I will be able to find the value of x. So what we have done, we have formed this equation where the number of remaining students should be lesser than the number of remaining seats. Now I have simplified this. I open the bracket and I took all the x components on the same side, and now I took x common, and now I found the value of x. Now I know that the value of x, the maximum value of x, right, as it says, it is greater than or equal to the maximum value of x, so that my student can sit, all the student will be equal to this, right? So with the help of this, I can find my total number of students that can sit alone. So let's see it in the code. So here's the code. So this was my first condition that we talked about. If we'll check whether it is feasible to make all the students sit or not, right? The total number of seats should be lesser than the number of students we have, and if should be greater than or equal to. If the total number of seats is lesser than the number of students I have, then we will return -1. And here we have second condition. If the total number of students that we have to sit, so the maximum number of students that can sit on each bench is 1, and then the number of students that will be sitting alone will be equal to our total number of students, right? And the feasible case we have already checked, so there's no need to check for the feasibility again. Here we have our another case. If k is greater than n, if number of benches is greater than number of students, then each student will be able to sit alone, right? In that case we will return n. And here we have implemented the condition that we have found, the equation that we have created, m into k minus n divided by m minus 1, right? This was the condition, this was the equation that we formed. Now why I have taken this long here, because the value can be up to 10 raised to the power 9. So to avoid going of integer out of bound, I have taken them into long. So it will be giving me the final value of x, and after doing this I'm turning my x into integer. I'm returning that, and now my x will be the total number of students that can sit alone, right? Total alone students. So this was our question 1. So now let's discuss our problem 2. The name of our second problem is bitwise operations. What does the problem statement say? Geek has an array ARR of size n initialized with zeros. He is also given k operations where each operation j is represented as ops of j equal to LRX. Each operation updates the element of the array in the following way. So initially we have given an array of size n which is containing n zeros. As it is initialized with zeros, our array will be initially containing only zeros. And we also have another array operations which is containing k different operations, and each operation is containing 3 variables l, r and x. So for each I in the range L to R, perform the operation array of I equals to array of I XOR X. So for in this operations array, for each L and R, we have to perform XOR operation for all the elements from L to R. We'll be doing array of I XOR with X. Your task is to determine the final array ARR after processing all operations and return it. So what we have, initially we have given an n, and n is the size of the array that we have, and initially we have n zeros in that array, 0 1 0 2 up to n zeros we have. And we have given another array ops which represents some k operations, and in each operation we are having 3 variables l, r and x, in which l and r is a range. This represents a range, and in this particular range we have to perform our XOR operation, perform XOR with our given x, with x, right? So from for each operation for the given L to R, we'll be iterating through L and R, and we have to perform the XOR operation for all the elements falling between L and R with this x. Now let's take an example. So in this example, we have given n equals to 3, and we have an ops array of k equals to 3. So we have 3 operations, and we have all 3 different values in all 3 operations. So initially our array will look something like this. containing 4 zeros. And after performing our first operation, so as this L has value of 1 and R has value of 3, and these numbers are based on one based indexing, right? So the index will be, it will point at index 0 and it will point at index 2. So up to, from index 0 to index 2, we have to perform XOR with this value 2. We have to perform XOR with this value 2. Now what we will do, if we perform XOR of any number with 0, XOR of any number x with 0, it will give with that particular number, right? Nothing is changed. So from 0 to 2, from 0 to index 2, all numbers will become 2. So 0, 1, 2. So it will become 2, 2, 2 and 0. Now what we have to do, we have L equals to 2 and R equals to 4 and our X is also 4. So its respective index will be 1 and its index will be 3. So we have to perform from index 1 to index 3. So XOR operation between 2 and 3, what we'll get when we perform XOR between 2 and 3, it will give me 1. So 2, 1, 1 and 3. We have to perform XOR between 2 and 4, right? Not 2 and 3. So 1, 0 and 1, 0, 0. It will be 1, 1, 0, which is equals to 6. So what we will get? Our first number will remain as it is. So index 1 will become 6, index 2 will become 6 and index 3, 0 XOR operated with 6, it will give 0 XOR operated with 4, it will give me 4, right? Now I have another values, L equals to 1, R equals to 4 and X equals to 6. So L equals to 1, R equals to 4 and X equals to 6. Now let's perform these operations. So index 0 to index 3, 0, 1, 2, 3. Okay, we have to perform in the whole array with this 6. So what we'll do, what we will get when we perform the XOR of 2 and 6, it will be 1, 0 and it will be 1, 1, 0. So what we'll get, 1, 0, 0. We'll get 4. So it will be 4 and 6 XOR 6. When we perform XOR between same number, it will give us 0 and 0 here. So XOR operation between 4 and 6, what will it give? XOR operation between 4 and 6, 1, 0, 0 and 1, 1, 0. We will get 0, 0, 0. It will also be 0. No, it won't be 0. Sorry, 0, 1, 0, 0, 1, 0. It will be 2. Right, so our final answer will look something like this, 4002. What was our output? Our output is 4002. So that's what we have to perform. We have to perform XOR with the given x of each array of I for I is in the range L to R. Right? So first thing, how can we approach with this question? First thing that comes to our mind is our basic brute force approach. So in the brute force, initially we will firstly create our array of n zeros. Let's say our n equals to 4. So we will create first array initiated with zeros. Now we will iterate through our operations array. So it will run from 0 to k, right? And in this we will run another for loop for L minus 1 up to R, right? And in this we will perform XOR with the given x. Let's say it is running for some index j, so we will do array of j XOR with x, right? And after that we will be returning our given array, right? This was the brute force. So what will be the time complexity of this brute force? As we are iterating through our operations array, this loop will run k times, right? This is the size of our operations array. k is the size of our operations array, and this nested loop, this loop we are running from L to R, right? So this nested loop will run from L to R. What can be the value of L to R? My L to R can have the maximum value of n, right? L can be 0, L can be 1, and my R can be n plus 1, right? Sorry, not n plus 1, only n, right? As they are based on one based indexing. So my time complexity will be k into n, which is really large, right? As if the size will be 10 raised to the power 9, it will become 10 raised to the power 9 to 10 raised to the power 9. We can surely optimize this, right? Now, to optimize this, what we will do, this thing we should do, right? We have to iterate through operations array to get each operation, right? We can't get each operation without iterating through our operations array, but we can surely remove this step in which we were iterating through our L to R, right? How we will do this? To iterate through, instead of iterating through L to R, instead of doing this, we will use difference array concept. Now, what is difference array concept? So as we were iterating through L to R, we were updating each value from L and L plus 1, now L plus 2 up to R, right? That's what we were doing. But instead of this, we will just change the value of L, right? And let's say we have to increment the bit. We just found that the XOR, when we will do the XOR, this particular bit, let's say second last bit, will be incremented. So we will just perform the increment at the Lth index, and at the R minus 1 index, at the R plus 1 index, we will decrement that particular bit. So when our final array will be formed, we will just use the concept of the prefix sum, and my final array will be containing that particular integer value. So on which array we will perform this difference array concept? We can't perform this on the integers, right? Because integers we can't directly access. As we are performing XOR operation, we will be dealing with the binary numbers, right? Some 1010. So what we'll do, we'll create an array of array which will contain n arrays, or instead of n we can say n plus 1 arrays. We will contain n plus 1 arrays of what size? Of size 32. Why size 32? So for each number from index 0 up to index n minus 1, right? Or we can say from position 1 to n, it will be containing 32, it will be containing n arrays, n plus 1 arrays of size 32, right? Why 32? Because 32 is the number of bit size that we have. Our numbers will always, our normal integers, or we can say natural numbers, lies from 0 to 32 in the bit size. So each array of size 32 will be containing zeros and ones, which will be representing the particular integer that will be there in the place of that index. So initially, as our array will be containing all the zeros, so we will initiate it with all the zeros, right? All the bits, all the 32 bits will be 0, and when we will perform our first XOR operation, what we will do? So while performing our first XOR operation, we know that as all the elements are 0, we will just increment that particular bit which has 1 as set bit in that particular XOR value I'm performing it. Let's say x has value 101, so we will increment this bit right? And I will increment this bit. So let's say we have a LRX pair of 3, 6, and let's say 5. So what we will do, we will have 1, 2, 3, 4, 5, 6, 7. So here we have this 5 represented, right? And all bits, we currently, all my bits will be 0, right? Currently all bits, this is the size of the array, and currently I have 32 bits, all are 0, and I'll perform bitwise operation with this 101. So what we will do, as the range we have is from 3 to 6, so I'll go to the index 3 and make our last bit 1, and second last bit is 0, there's no need to increment it, and third last bit as 1. And now I'll go to the index 5, sorry, index 6, 6 plus 1, let's say it is of size 9. Now I'll go to the index 6 plus 1, which is, so in this L and R are representing particular index. I'm not talking about one-based indexing, I'm talking about their respective index. So let's take one-based indexing so it will be more clear. So currently they are in one-based indexing. I'll convert them to their particular index. So the index will be 2 and 5. So at 2, what I'll do, I'll increment this bit, and this bit will remain same as here is 0. Here's a set bit, so I'll increment this bit. Now, so this was our lower limit, and from upper limit, what I'll do, at 5 plus 1, at index 6, as this bit was increased, I'll decrement this bit, and here I'll decrement this bit, and this bit will remain same. So why I have done that? So when I'll perform the prefix sum on this array, all the numbers from 2 to 6, what will happen to them? They will become, this bit will get increased, this bit will get increased, and I'll just make them equal to their, I'll just add their previous bit to them, right? So here, what was its previous bit? It was 1. It will get added to it, it will become 1. So what was its previous bit? It was 1, and initially it was 0, so its previous bit will get added to it and it will become 1. Similarly here, what was its previous bit? It was 1, so it will become 0, right? And here it will also be 1. What was its previous bit? It will become 0, and similarly it will be 0 0 0 here, it will be 0 0 0 here, right? So you can see my range from 2 to 5 will become updated according to the given XOR condition. And after updating them, I'll have all the bit arrays for 1 to n, or I can say 0 to n, right? I'll have all the bit arrays representing 32 arrays of size 32. Now each bit array will be containing some binary representation, and with the help of that binary representation, I'll turn that binary representation into the given integer, and I'll form my final answer. And that, after forming that, right, I'll form some decimal value from this. Let's say I form 9, here from I form 8, here I form 7, and here I form 5. So this will be my final array that I will be returning, right? So this was the approach. That's how we will be doing this. We can't normally iterate from L to R because it will give runtime error, because its time complexity was O of n into O of k. But what will be the time complexity of this? As in this, firstly we will run a loop from k, and in that k loop we will run a loop up to 32, right, to update all the 32 bits in all the k arrays. for all the k operations. And now we will run a loop up to n, and in this loop up to n I'll have 32 bits, right? I'll check for all the 32 bits I have, and I'll update them according to the previous bit. And while updating them according to the previous bit, I'll create my number, my decimal number will be formed, and I'll be storing that it in my final answer array, and after that I'll be returning it. So here it was running for 32 into k times, and it will be running into 32 into n times. So it was of k, it was of n, so its time complexity will be O of n plus O of k. So now let's see the solution of this problem. So here's our function. Firstly, we have created our vector of size n plus 1, and we have created 32. We have, for each index, I have created an array of size 32, which is initialized with 32 zeros. Right? Currently all elements are 0, so we have initialized it with 32 0, representing binary representation of our 0. So now I'm traversing my operations array, traversing operations. Now here I have created my LR index. This is the lower limit, this is the upper range, lower range limit and upper range limit, and this is my XOR number with which I'll perform my XOR operation. Now I'm accessing the given array, the bit array that I have formed of size 32. Now here, if x is containing set bit at a particular jth position, then I'm incrementing that particular jth position for that lower range, and I'm decrementing that for my 1 plus upper range, right? Because from lower to upper range is included, so I'll decrement just after my upper range, which is 1 plus my upper range. And after doing that, my loop is ended. Now I am creating my final array, which will be storing my final answer. I've created a res array of n elements starting with all the zeros. Now I'm iterating my array of size n, and here I have iterated for 32, 0 to 32. I'm iterating from, right? So I'll be iterating my bits array for all the n numbers and all the arrays that each index is containing of size 32, and I'm checking if my current index is greater than 0. If current index is greater than 0, then I will be adding the previous bit value for that particular index, right? Because if it is equals to 0, then I won't be able to access its previous index, because 0 is my first index. Now why I'm doing this? Because to change all from L to R, right? Because my L was containing the updated value, but all the range from L to R is not containing that updated value. So from L to R, I'll update all the elements. All the elements will get updated with the help of this, and after R plus 1 up to N, all the elements will be also updated. Yes, from R plus 1 to N, all the elements will also be updated. Now here I'm checking if the current bit is 1 or not. If the current bit is 1, then I'm making that bit in my final array as 1. For that particular index, I'm making that particular bit as 1, and it will be forming my final decimal value, right? Because after this, my bits array for that particular index is now sorted. It is now containing its desired binary representation, and with the help of that binary representation, I'm forming my decimal number, and the rest of I will be containing its desired number, and at the end I'm returning my res array, which will be storing the final answer. So now let's discuss our problem 3 of this weekly contest. So the name of our problem 3 is subset XOR. Let's read the problem statement. You are given an integer n. Select a subset of integers from 1 to n, both inclusive, where each integer can be chosen at most once, such that the XOR of all elements in the subset is equal to n. The size of the subset is maximized. If there are multiple subsets that satisfy these conditions, choose the subset that has the lexicographically smallest order. So we have given an integer n, and we have to find a subset from the integers 1 to n such that the XOR of that subset, let's say we have some numbers from a1, a2 up to some ak, right? We don't know how many numbers we are going to have. So out of these numbers, the XOR of all these numbers, the XOR of all these numbers needs to be equal to Rn, the number which we had initially, right? And we have to form this subset such that the size of the subset is maximized. So we have to include as numbers as we can from this given range of 1 to n, right? And if there are multiple if there are multiple subsets that can be formed, so in that case we will be returning our lexicographically smallest. Like if we have some subset like 1 3 4 8 6, so this is one, and this is other. Let's say we have these two, then in this case we will be ignoring this one because it has 6 in it and it is lexicographically smaller than this subset. Then we will be returning this subset, right? And we can't return this subset in another way, right? Because it will change its lexicographical order and it will make it lexicographically greater than its initial position. So to make it lexicographically smaller, it needs to be arranged in ascending order, in increasing order, right? Here we will have the smallest, then greater, then greater, then greater, and then the largest, right? So we have our integer n, and we have to find all the numbers from 1 to n, which forms a XOR of the given number n. Let's take an example. So here we have given n equals to 4, and here I have calculated the respective decimal value, sorry, not decimal, binary value of all the given integers here. And now I have to find the subset from these four numbers such that the XOR of all the numbers will be giving me this n. So let's find the XOR of all these numbers firstly. So let's say in the XOR, what we will do, the XOR of two numbers will be 1. If we take XOR between 1 and 0, it will give me 1. But if I take XOR between 1 and 1, it will be 0, and XOR between 0 and 0, it will also be 0, because the XOR between different bits is always 1 and the XOR between same bits is always 0, right? So by this I know that if I have even number of even if I have even number of set bits, then their XOR will be 0. So here I'll be have a 0, and here as we have two set bits, then it will be a 0. So from here we will have a 1, and here it will be a 0. So the XOR of 1 to 4 will be 3, right? Sorry, it will be 4, not 3, it will be 4. So what we have to find? We have to find the subset which has its XOR as 4. So our subset will be 1, 2, 3, 4, numbers from 1 to n itself. That's what we will return. And now take another example. Here we have number 3, n equals to 3. So the binary representation of them will be like this: 0001, 0010, and 0011. So here, if it takes the XOR, it will be 0, it will be 0, 0, 0. So the XOR between 1 to 3 will be 0. So now if I need to form a subset which has a given XOR of 3, what will I do? Let's say if I take the XOR of this 1 and 2, what will it give me? It will be 1 and it will also be 1. It will give me 3. And now if I take between this 2 and 3, it will give me 1. And if I take between this 1 and 3, it will give me 2, right? This one cancel out, forms 0, and this 0 forms 1. So the subset that will have its XOR value as n, where our n is 3, will be 1 and 2. Right? So what we are doing in this, we are taking one thing we can do. We can consider all the subsets and we can find them one by one, right? But it will be really time consuming. So as we have to find XOR, firstly we will try finding a pattern in this XOR. Let's take a bigger value. Let's take, we have our n equals to 10. So firstly, let's find what will be the XOR of all these values 1 to 10. So we know that if set bits are even, then XOR is equals to, so then XOR is equals to 1 for even, right? No, the XOR is equals to 0 for even, right? And for odd, it is 1. So here if we see 2, 2 and 1, it will be 1. And here if we will see 2, 2 and 1, it will be 1. And here if we will see 1, 2, 3, 4, so it will be 0. And here if we see 1, 2, 3, it will be 1. So it will give me a value of 11. So the XOR between 1 to 10 will be 11. Now I have to find the subset which will be having a XOR of 10. And what information I currently have? I currently have that the XOR of 1 to 10 gives me 11. So what we will do, we will compare this XOR with our desired XOR, right? Because what numbers we can take? We can take the numbers from 1 to n only, right? So in this case, what we will do, we have our 11, which is the XOR of 1 to 10, and now we have our desired XOR, which is 10, right? My desired XOR, which is 10. So what will be the difference between these two XOR? What will be the difference between these two values? What will be the difference between the bits of these two values? How can I find the difference between the bits of these two values? I will use XOR to find the difference between the bits. Why? Because what does XOR give me? If there's a difference between any two bits, then it gives me 1. Yes, there's a difference. But if there's no difference between any two bits, like here, if both are set bits, then it will give me 0. And if both the bits are 0, then it will also give me 0, right? So if I have to find the difference between two bits, if whether there's a difference between any bit or not, in that case I'll use XOR. So let's find difference between this 11 and 10. So if I do XOR of this 11 and 10, what will I get? Here's my 10 and here's my 11. So I'll get this 0 1 1 1 1 0 0 0 0 and 1 1 0, right? So I'll get 1. So this 1 I'm getting. So now I have the difference between the difference of bits between my desired XOR and the XOR I'm getting. So now if I want to change my current XOR, right, current XOR, which in this case I have 11, to my desired XOR, which is n, and here in this case I have 10, and there's our value. What will it be? It is I'm getting as 1. So now if somehow I'll be able to remove this 1 from this 11, then I can make my XOR value as 10. But which integer value, which integer value from this given range of 1 to n should I remove to remove this one? As in this case it is 1, we know that if we remove 1, then it will make it clear, but it can be some other value, right? It can be some 1011. In that case we will get confused. So let's see. So what we will do here, if I takes the XOR of this difference and this, what will it give me? Let's say the XOR representation of 11 will be like 1011, and here we have 0001. So if we take XOR of this value of my current XOR and the difference between this desired XOR, then I will get my desired XOR, right? Then it will be 1010, which is equal to 10. So if somehow I will be able to take one more XOR of this one, if somehow I'll be able to take XOR between my current and current with the XOR of the difference of bits, right? Or I can do the opposite. If I can, what is my current? My current consists of XOR between 1 to 2 to 3 up to Rn, right? If somehow I will be able to remove my difference of bits from this current XOR set, right? Like here the difference of bit was 1. If I'll remove this one, then what will happen? Then here in this case this one will get removed. If I remove this one, then what will be the XOR value? Here 1 1 1 1, it will give me a 0. Now what is my XOR value? It is 1010, which is equal to my n, right? Why is it happening? Why does this happen? Because I found the difference between the bits of the XOR I was getting and the XOR I wanted, right? And the difference of bit, like here it was only our last bit was different. So if I didn't consider that last bit, right? Because why is the difference I'm getting? Either my XOR I'm getting is 0 or the XOR I'm getting is 1, right? So it is different from my desired XOR. So what I have to make, what can I do to make it equal to my desired XOR? Right, here we know that when set bits are even, our XOR is 0, and when set bits are odd, our XOR is 1. So if the set bits would be odd, then I need to make the set bits at that place equals to even, right? So I have to remove, I can either add that set bit or remove that set bit. So I can't add another value to my 1 to n, right? As I have the access of only 1 to n, I can't add another value. So in that case I'll remove that particular value, right? Because like we have some number n, and in that n we have 5 set bits. In this fourth value, this third, 2 1, and here we have some 6 set bits, here we have some 2 set bits, and here we have some 8 set bits, right? We have taken random numbers. So what will be this XOR? So here it has 5 set bits, so it will be 1. Here if it has 6 set bits, then it will be 0. Here if it has 2 set bits, 2 will be lesser. Let's take 12. So here if it has 12 set bits, then it will be 0. And here if it has 8 set bits, then it will be 0, right? So in case like if I if I wanted one here and one here, right? I wanted one at the place of these two zeros. So if I had, instead of 5, if instead of this 6, if I had 5 set bits here, then what will be the value of the XOR at this place? It will be 1. And instead of this 12, if I had 11 set bits here, then what will be the value of this 0? It will be 1, right? And similarly, if I want 0 at this place, here I want 0. So if I reduce this 5 by 1, it will become 4, right? What is this indicating? This is indicating the number of set bits from 1 to n. So if I reduce this 5 by 1, it will become 4. Now it is even. So if the set bits would be 1 lesser, then it will be 0, right? So what I will do, I'll find the current difference. I'll find the difference of the bits of my desired XOR and the XOR I'm getting, desired XOR, and my XOR of 1 to n. XOR of 1 to n. I'll take their XOR difference. What is the difference between their bits? Now, from that bit, I'll form a number, and if I remove that number from that set, then it will reduce the value of all the set bits by 1, and it will make my XOR I have equal to my desired XOR, right? And as my desired XOR is equal to n, and XOR that we have is from numbers of 1 to n. So the difference that I'll be taking, the difference that I'll be calculating will always lie from 0 to n, right? Because it can't exceed it, because it is taken between what? N and a XOR which is taken from number 1 to n, right? So if it has some numbers like this, 1011 and 1000, so it can't exceed it, because here the XOR we calculated from 1 to n will be having all the bits that is existed up to now, right? Because if we take further bits, they would have remained 0, right? And if we take the XOR, it would always be lying somewhere between 0 to n. So if we remove that particular element from our subset, that particular element which is formed by taking the difference of the bits, if we remove that element from the subset, then our subset will be equal to, then the XOR of the subset will be equal to our desired XOR that we want. So how we will do this? Firstly, we will create an array, right? For example, if we have n equals to 7, we will create an array of 1, 2, 3, 4, 5, 6, 7. Now we have all the numbers from 1 to n, right? We have created an array, and with the help of this array, what we'll do, we'll find the XOR of all these numbers from 1 to n. XOR of 1 to n. Now the XOR of 1 to 7, it will be equals to 0. The XOR of 1 to 7 will be 0, right? You can calculate it if you want. Now if we do XOR of 1 to 7, what we are getting is, we are getting it as 0. And what will be the XOR, what will be my desired XOR? My desired XOR was 7, and what I'm getting 0. So if I take the XOR value between these desired XOR and the XOR I'm getting, it will be, so if we take the XOR of any number with 0, it will be that number itself, right? So the XOR will be 7, and what will be my output? In my output, I'll be returning all the numbers except this particular element. So it will be from 1, 2, 3, 4, 5, and 6. I'll be ignoring 7, because if I remove 7, this XOR 0 value will become equal to 7. Let's test whether it is correct or not. So 1, 2, 3, 4, 5, 6, 7. it is 1, it is 1 0, it is 1 1, it is 1 0 0, it is 1 0 1, it is 1 1 0, it is 1 1 1. Right? We have to ignore the 7 as of now. So it will be 1, it will be also 1, and it will also be 1. So what we got? The XOR of 1 to 6 we got as 7. This is what we wanted, right? So this was our question. What we have done, we will firstly create our array of the numbers from 1 to n, and from this array we will calculate the XOR of all the numbers from 1 to n, and in that XOR we will calculate the difference between our desired XOR and the XOR that we are getting, and after calculating that difference we will remove the difference from the array that we have. Right? Now let's see the solution. So here's a solution. Firstly, we have created an array of size n, right? And we are inserting all the elements from 1 to n by running a loop from 0 to up to n minus 1. And now we are calculating the XOR of all the numbers from 1 to n. Their XOR we are calculating, and we are checking if our XOR is equals to n, right? Like in the case of 1 to 4, our XOR was equals to n. So what we do, we will return our ANS itself, our answer itself, the array we have formed from 1 to n, right? If the XOR of 1 to n is already equals to our desired XOR, then we will return our 1 to n. Now, what we are doing else, if its XOR value is not equals to n, we have calculated a value which is the difference between our XOR we have found and the XOR we want, and we are creating another vector in which we are iterating through our original vector from 1 to n, and if current number is not equals to that difference, we will push that in our new vector, right? So all the numbers except this difference will be pushed into our new array. So, and what we'll do at the end, we will return our new array which will be containing all the numbers except that difference, and the XOR value of that array will be equal to our desired n. So this was the question 3. So now let's discuss our fourth problem of this contest. The name of our fourth problem is minimum k for valid XOR combinations. What does the problem statement says? You are given a sequence of playing cards with numbers written on them represented by an array ARR. You can select any contiguous sequence of cards. Cards must be consecutive, and compute the bitwise XOR of the numbers in the selected sequence. A sequence is considered valid if the XOR of its number is at most k. The task is to find the smallest value of k such that there are at least x valid sequences. So we have given an array ARR, and we have to select some contiguous sequence, right? Some subarrays we have to select and compute the bitwise XOR of the numbers in selected sequence. A sequence is considered valid if its XOR is at most k. So if the sequence that we have and we compute the XOR for that particular sequence, and if the XOR value of that sequence is lesser than or equals to k, then we can consider that particular sequence as a valid sequence. The task is to find the smallest value of k such that there are at least x valid sequences. We have to find the smallest value of k such that there are at least x valid sequences. So what does this mean? Let's say we have given an array A with some integers a1, a2, a3 up to an. So it says that smallest value of k we have to find such that it has at least x valid sequences. So we have to find for each value of k there needs to have at least x subarrays, right? At least x valid subsequences. So we have to find value of k such that there are at least x subarrays which are having a XOR of that k, and this k needs to be minimum, right? We have to find a k such that it can have x subarrays. It can have x subarrays, at least x subarrays. So x or more subarrays having their XOR value as k, their XOR as k, and we have to minimize this k, right? Their XOR value as k or lesser, sorry, as k or lesser can work, right? So we have to find at least x subarrays having XOR of k or lesser, and we need to minimize this k as much as we can. So now let's see. Now if we have an array, right, the array A we have considered it is having some integers a1, a2, a3, a4 up to an. So in this array, if we select a value k, it needs to have at least x subarrays which is having a XOR value of k or lesser than k, right? K or lesser than k. So let's say if my value of k lies somewhere here, right? My value of k lies here. So all the subarrays of this array which are having the XOR in this range from 0 to k, right? K or lesser, all will be considered as valid subarrays, right? And if r k is somewhere here, so all the subarrays that is having their XOR value from this 0 to this k will be considered a valid subarray, right? Because they will be having a XOR value of k or lesser. So by this we can say that as my value of k will increase, as the value of k will increase, number of subarrays will increase. Number of subarrays will also increase, right? Because right, here when the value of k was smaller, it was having some x subarrays. Now let's say it has some y subarrays, but this x number of subarrays is also included in this y subarrays, right? Because as this, let's say k1 and call this k2, this k1 is lesser than this k2, this k1 is lesser than this k2. So all the subarrays that are having a XOR up to this k1 will also fall into this k2, right? They will also be having a XOR lesser than this k2. So we can say that as value of this k will increase, the number of subarrays will increase, right? So we have to find the minimum value of k, right? Why minimum? Because if I return something like 10 raised to the power 9, the maximum value that we have, if we returns that, then the number of subarrays would be x or more, right? Because let's say 10 raised to the power 9 is the maximum value that our number can have. So the maximum value, so the maximum subarrays will be always greater than this given x, or they will be maximum subarrays that will form. It will be equal to the total subarrays, right? Total subarrays that we will form if we return a very large number. If it returns a very large number, the total number of subarrays will be equal to the number of subarrays that can be formed. So, because of that, I have to return the smallest k so that the number of subarrays that can be formed will be at least x. If they are greater than x, that would also work. So, for that, we need to find our k and what can be the range of the value of k. And as we know, the XOR value of any given numbers will always be greater than or equal to 0. So our k can start from 0, and what will be the largest value our k can have? So for the largest value, if let's say we have an array A and it has numbers a1, a2, a3, a4 up to some an, and its largest number is some a7. A7 is the largest number it can have, right? So if we take the XOR of this whole subarray, what can be the maximum XOR that we can get? Let's say this A7 is represented as something like this 10111100. This is the binary representation of the maximum number of this array. Right? So what can be the maximum XOR that we can have? So in the XOR, we know that, let's say we have some empty bits 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, and let's take one more. So we have some empty bits, and if we take XOR, firstly we will start from the 0, and if we take the XOR, and as this is the largest number, our most significant bit will be this one, this bit, right? It can't have other bits as 1, right? Because if other number would be having another bit as 1, then it will become largest. So as currently we are talking about our largest number, it will have this bit as most significant bit. It will be having most significant bit, right? And if we take its XOR with other numbers, we can't exceed this bit, right? Other bits would always remain 0. Other bits on the right would always remain 0. The change that will happen is either on this bit or either on all the bits that are present on the right. So what is the maximum number that we can get? The maximum number will be 1 1 1 1 1 1 1 1, right? So if all the bits on which we are performing XOR become set bits, that is the maximum number that we can obtain. So we can say that it will be lesser than 2 into our largest number, right? So because what will be 2 into this number? If we shift all the bits to the left, if we shift all the bits to the left, then it will become twice, right? If we shift this bit here, this bit here, this bit here, shift each bit on left by once, then it will become 2 times. So the value of k will always lie from 0 to the 2 into our largest number, because the XOR value can't exceed, XOR value of an array can't exceed 2 into its largest number, and XOR value can't become lesser than 0, right? So this will be the range from where our value of k will lie. So after finding this range, what we can do, we can, now here we have a range and we have to find the k such that it has at least x subarrays, at least, right? X subarrays which are having a XOR of this k. So what we will do, we will check for different case whether it is feasible or not to have x subarrays. So let's understand this more. So here we have a number line, and here we have 0, and here we have 10 raised to the power 9. So if let's say we start from the middle, if we start from the middle and we say the number of subarrays from here to here, let's say this is our current value of k, the number of subarrays from here to here is lesser than x. If the number of subarrays that we can found from this number is lesser than x, then what we can do, as the number of subarrays is lesser than x, then we need to find more subarrays. So to increase the number of subarrays, what we'll do, we will increment this given k, right? So that we can have more subarrays. Now we will increment this k. Now it will be including the previous subarrays, and now it will include some new subarrays too, right? And now we will check if its value, if the new number of subarrays that we have found from this 0, let's call it k1 and this k2, from this 0 to this k2 is greater than or equal to x or not. Let's say they are greater than x, then what we can do, we can surely find a smaller k, right? As the number of subarrays is greater, we will try to find a k which is smaller, right? We have to find the minimum k. So we will just shift our k towards the left. We will now reduce our k. So where we find our k, after we find our k between this range, now we will reduce our k. Let's say our k is here, and let's say we found some exact value of x. Let's say here we have the number of subarrays is exactly k, and if we are moving here, it is increasing x, and if we are moving here, it is lesser than x. Then we will return this particular k, right? So you all might have got the idea that we are going to use binary search here, right? We are going to use binary search. So in the binary search, we will have the low and high. So low and high we have already discussed. It will be the low and high represents the range where our mid will lie. So low will start from 0. This is the least value that our k can have, and high will start from the 2 into max element. Right? This is the largest value that our k can have. And we will similarly iterate for our k in the while loop while low is lesser than high, and if somewhere number subarray count is greater than x. If the subarray count is greater than x, then what we will do? If the number of subarrays that we have found, is greater than x, then what does it mean? If let's say our k is here, and the number of subarrays is greater than x, then we will reduce our k. Then we will shift our k to the left. Now here our k will lie, and if the number of subarrays is greater, let's say n is the number of subarrays is lesser than x, then in that case we will move our k to the right. So if the number of subarrays is greater, in that case we will reduce our k, right? Because we have to reduce the number of subarrays. So we will do, let's say k, we will be representing our k as mid. We will do mid equals to, not mid, we will change. So in binary search, when we have to move our mid, we have to decrement our mid. We will do what? We will make our high equals to mid, and we will do this, and in the opposite condition we will make our low equals to mid plus 1, right? And now what we have to do, we have to now find this subarray count. This is the main thing that we have to do. If we are able to find this subarray count, then the question is done. Then we can simply implement our binary search, and we will have our final answer. So how we will find this subarray count? So to find the subarray count, now our task is to find the subarray count for the given XOR of k or lesser, right? So we have to find our number of subarrays for with XOR k or lesser, right? We have to find number of subarrays with a XOR of k or lesser than k. Now what we can do? Firstly, the first thing that we can do is simply implementing our brute force, calculating the XOR value for all the subarrays that we can form, and among those XOR values, we will count which XOR values is lesser than k, and we will return that particular count. But for this function, what will be our time complexity? Our time complexity going to be O of n square, and if we will implement it, it will give me a time limit exceeded error. Now what we will do, we have to implement it in an optimized way, and we have to perform optimization on this. So how we are going to optimize this? We are going to optimize this by using the XOR methods that we have. So for each XOR, we have a method for in a XOR of a subarray, we have a property. So XOR in a range of, we can say, L to R, right? Where L is the lower range and L is the upper range, where L and R both are indexes. So XOR of a subarray from L to R is equal to the XOR of all the numbers from index 0, right? Index 0 to L minus 1, and XOR operation with all the subarrays from index 0 up to R. If we takes the XOR from starting of the array and L minus 1 just before our starting index, and if we take the XOR of starting of the array and up to our last index, it will give me the XOR of that particular subarray. This property we are going to use because we can't calculate the XOR of each subarray, right? So for this, what we will do, we are going to use try to implement this method. Now our try will be containing of two nodes. We'll create a try of two nodes. Each node will represent 1 and 0. By 1 and 0 we mean that each node will be representing either, there is, let's say, initially we have this node, and let's say we have this node for 1. Currently we have first bit as set bit, and now after this we will be having, here it represents 0, here it represents 1. So if next bit is a set bit, then it will be true. If next bit is not set bit, is a 0, then it will be true, right? So here, let's say if the next bit is also set bit, so it will be 0. And similarly here we will have other nodes. Let's say here our next bit is not a set bit. Here let's say our next bit is not a set bit, then it will be 1. And similarly here, if our next bit is set bit, then it will be 1, and if it is not a set bit, then it will be 1, right? Similarly we'll be counting all the set bits for all the number. With the help of this try, we will be representing our binary representation of the prefix dot that we have found. So we are going to create a prefix XOR. And with the help of that prefix XOR, we are going to find our particular XOR for each subarray, XOR of subarray, right? XOR of subarray, and number of subarrays we will find with the help of that too. So in this try will be storing all the numbers in that subarray which are having their particular bit, which is that particular bit is present or not. If that particular bit is 0, let's say here in the question we have range of 10 raised to the power 4, so we can create 20 bits, right? 20 bits in the 20 bits, from 20 bits we can go up to some 10 raised to the power 6. So 20 bits would be enough. We don't need to create 32 bits. It would be too much. So if we create 20 bits, so it will be containing 20 nodes, right? 20 into 2 nodes, and each node will be indicating whether this particular bit is set bit or not for a given number, and it will be storing a count for how many numbers this particular bit is present or not. If like this bit is set bit, then it will be storing, and if this bit is not a set bit, then it will have value of 1, and if this bit is present, if this bit is set bit, then it will have that particular value, right? it can be quite confusing. Let's consider an example 101. Let's say we are going to represent it in the try. Then firstly we have two bits. This represents 0, this represents 1. So firstly we have 1, so it will be true. It will be holding some value and it will be initialized with 0. Now with this, as it will have no other childs, as this bit is not currently true, so it will have another child, here 0, here 1. So next bit is 0, so here it will have value 1, here it will have value 0, and next bit we have here 0, here 1. So our number that we taken was 101. So 1 0, here it will be 1 and here it will be 0. So if we iterate this try, we will get the binary representation, which is 1 0 1, right? That's how we are going to use our try, and with the help of this try we are going to iterate through all of the subarrays, and we will be finding the XOR for all the subarrays. Now we're going to use prefix OR. How our prefix OR will be helping? So in the prefix OR, we will be storing our prefix OR. Prefix OR will be representing what is the XOR up to current number, right? Let's say we are on some I, it will be storing what is the current XOR from up to 0 minus 0 to I minus 1. So with the help of this prefix OR, if let's say this prefix OR is 1010, and now what we have to do, what we want to do, we want to minimize this XOR. If we want to reduce this XOR, right? So here in this bit we will check for this bit. If this bit is 1, then we will check if the for the 0th bit, because if the bit in the number is 0, then what will the XOR will give me? The XOR will give me 1, and if the bit is 1, then the XOR will give me 0. As we want to minimize our k, we want to minimize our XOR, so for that we will go for minimum. We will check for 0, and if this bit is 1, then it can also have a lower value of XOR, then we will also consider this. But if somewhere in the prefix OR we have 0, if somewhere in the prefix OR we have 0, then as we want to minimize it, we won't be considering 1, right? So we won't be considering 0, we won't be considering a XOR of 1. We don't want our XOR as 1 because it will increment it, it will increase it. So we will be considering the value 1, because 0 XOR 1 gives me what? 0 XOR 1 gives me 1, right? So we don't want 1. So sorry for the confusion, we will be considering 0, not 1, because if we will consider 1, in that case we will get our XOR as 1. So we want to reduce our XOR, but it will increment it, so we won't be considering 1 in the case of 0th bit, and we will be considering 0 only, right? That's what we are going to do. That's how we will calculate all the subarrays by comparing their XOR values with a try. Now let's see the solution. So here we have created our try, right? Try, we have initiated it with two nodes. We have called them children nodes, children 0 and children 1. Currently all are initiated with null, right? And we have created scnt, which is storing the count for that particular bit, how many number is having that bit. And here we have performed our insert function. If we are inserting a prefix OR in that try, and for that we are running a loop from 0 to 20. We are accessing all the 20 bits, and here we are performing AND function to check whether our current bit is set bit or not, and we are storing it in the respective child. Bit is representing our current bit, whether it is 0 or 1, and it will be storing at that respective index. And now are moving our node and now we are moving our node to the next bit with the help of this, right? If let's say it has 1, so it will store, it will make, it will go to our children bit 1, children bit of 1, children of 1, and it will create new node there, and here it won't be null, and after creating new node it will move to this node, and after that it will increment the counter, right? Because we have found this node. This is what we are doing in the insert function, and here we have implemented our count subarray function. Let's consider it later. Firstly, let's see our, this is the binary search implementation that we talked about initially. Here's our low, we initiated it from 0. Here's our high, we initiated it from 2 into max element, 2 raised to the power max element, right? This can be the maximum value of our high, and here we have initiated our result from 0, and here we are calculating mid, and for each mid we are calculating number of subarrays, and if the number of subarrays is greater than x, then we are reducing our mid, right? Then we will be reducing k will be reduced if number of subarrays is greater than or equal to x, right? Because we can still reduce our subarrays, and if it is lesser than x, then we are incrementing our mid, right? And after that our final mid, we are storing our mid in the res when it is a feasible answer, right? In the case when it is either equal or greater than my x, then it is a feasible answer. At the time we are storing it in the res, and at last we are returning our res. So here we have implemented our count subarray function, and this we have created a prefix or a count and try not, and we have initialized a try, and we are inserting value of prefix or, we are calculating prefix or and inserting it in the try root, and we are calculating prefix or again, and we will be again storing it, again creating a try with it. Now here this is the main step, cnt plus, we are incrementing the number of subarrays that we are able to find. So how this function will work, here we have root, prefix or and k, and what we have done, we have initialized a try node with root, and we are running through all the bits, and if prefix bit is 1, for that we are calculating the prefix bit, what is the value of prefix bit for that particular bit, and we are also calculating the bit for that k, because we want to know what is the value of k that we have, whether it is 1 or 0, right, for that particular bit. And now we can have 4 cases, because for what we have calculated our bits for k, and for prefix, right? For each particular bit, let's say we have 0 0 1 1, we have 4 bits for each particular bit. We can have this as 0, this as 1, this as 1, this as 0, both 1 and both zeros. So in the first case, when these both are 0, then what we will do, if these both are 0, then our current kth bit is 0. Then as we want to reduce our k, as we can't increase, as we can't make our XOR more than k, we can't increment this k, our XOR value should always remain lesser than this k, right? Lesser than or equal to this k. So our XOR value can't go above this 0. So what we will do, we will go to the 0th bit for the numbers which are having the current bit as 0, right? We will go to that, and if there's no number which are having current bit as 0, then we can't move further. In that condition we will break. And in the case 2, when k is 0 and the prefix bit is 1, So as my prefix bit is 1, we need to decrement it, right? So we will go to our first bit so that it will become 0, right? And if it is possible, then we will go to the children of 1. If it is not, then we will break out of the condition. And here we have third condition. When kth bit is 1 and the prefix bit is 0, in that condition, what we will do, here we will check if children of 0 exists or not. If it exists, then we will insert its count in our res, and if children of 1 exists, then we move our node to the children of 1. Why? Because our kth bit is 1, the prefix bit is 0. So for the kth bit, as my kth bit is 1, so for all the numbers that are having that particular bit as 0, will be having a XOR lesser than 0, right? XOR lesser than our given k, right? Because that bit of the k is 1, and if any number is having, any prefix XOR is having that particular bit as 0, then we can say the XOR of those subarrays is lesser than our k. Then we will consider all of their count, and if it is not 0, it is 1, there are chances that in the future it can become smaller. So we are also considering the numbers which are having the current bit as 1, right? And here we have our fourth case. If both are 1, then similarly we will be considering our 1 bit, because our prefix bit is 1 and our kth bit is 1. So to make it smaller, our bit needs to be 0, as our prefix bit is 1. If the bit would be 1, then it will become smaller, right? Then our XOR will become smaller. So we will be considering bit with 1, children's with bit 1. We will be adding their count because it would have smaller. And if some numbers have that particular bit as 0, then it will give me a XOR of 1. But 1 can also have a XOR smaller than k. In the future, it can become lesser, right? So we will be also considering that. Here we have checked whether children of 0 exist. If it exists, then we are moving to it. This was our helper function. Here it is called. It will be returning final res, which will give me the number of subarrays with XOR value lesser than that particular k. And here we will be returning count, because we are calculating lesser than k. Here we have called mid plus 1, right? We are calculating number of subarrays for that mid plus 1. And here after adding in res, our res will be storing the final answer, and we are returning res. So this was our fourth problem of this contest. Now all the problems of our weekly contests are done. Thank you for watching.